Okay, this is a good hydrostatic force problem. This is a calculus problem. So we have this rectangular dam here. Here's our water level. The rectangular dam extends 8 feet down and or 5 meters down and is 8 meters long. We're going to calculate the hydrostatic force, the total force of water acting perpendicularly against this dam. So the first thing we do, set up our x and y axes. In this case, it's best to set our x-axis along the along the water's edge, and set the y-axis going down. So positive y goes down. That's the positive direction. It's much easier that way. Then we go down to some arbitrary y value. I've called it y star. And we're going to do a Riemann sum here for our total force. We pick out some small sliver here of this rectangle, call it some delta y thickness. Here it is blown up. So it's delta y thick, it's 8 wide. That makes this problem the easy version because we have a constant width. In general, our width will change as we go down and will depend on y. But in this case, our width is a constant. It's just always 8. Then the area of this little rectangle is 8 times delta y, length times width. Pressure depends on depth. The pressure of water at some depth is the density of water, which is 1, times g, 9.8 meters per second squared, times the depth d. Here my depth below the water is that little variable I called y star. So here's my pressure at that depth. Well, then the force just from this little rectangle here is that pressure times the area. So pressure times area. That's the force from just one little rectangle. We need to add up all of our little rectangles, so we do a Riemann sum. So technically, if we were to write this out in all the details, we would break this up into, say, n little rectangles, and we'd have the sum from 1 to n. And this would represent, say, the ith rectangle. So we're being a little sloppy with our notation here, but we know how Riemann sums work. So the total force, that says total, we'll be adding up all these little individual forces, which is pressure times area. So there's our sum. Then we take the limit as delta y goes to 0. That's the same thing as taking the limit as n goes to infinity, taking an infinite number of infinitely thin rectangles. This Arabic or Greek letter S, sigma, turns into a stretched out Arabic S. That's what the integral symbol really is. It's an S, it means sum. When delta y goes to 0, it becomes a dy, and we put in our limits of integration. The smallest value of y that made sense here was y equals 0 at the water line up to y equals 5. So then we just do this integral. 8, rho, and g are all constants. They can come outside the integrand. The antiderivative of y dy is y squared over 2. Plug in our top or bottom limit 0, so that all cancels out. And we end up getting 100 times rho, which is 1 for water. Remember, rho is mass per volume. So for water, that's 1 cubic centimeter per milliliter. G is 9.8 newtons. And really, if we're in SI units here, rho is 1,000 kilograms per cubic meter. So if we wanted to plug in numbers, we wouldn't plug in 1, we would plug in 1,000 kilograms per cubic meter to be in SI units if we want newtons. And G, of course, is 9.8.